All right, let's get it started. Okay, so welcome to Lecture 7 of 5323-7323 Mobile Sensing and Learning. Moving on. Okay, so course logistics for today. A1 grades are posted. The way that Blackboard works on this is that basically whoever turned in the assignment has all of the comments for the way that I went through it. Okay. And if you guys as a team, if anybody wants to meet with me, you're welcome to. Set up a time or meet with me during lab, or if you want to do it in my office, we can meet in my office, and we can talk about that or new projects or whatever you want. Schedule something with me. Office hours, just drop by. Okay, happiness. So whoever turned it in, that's how you can get the comments for it. I think the average was about an 84%, so 8.4 points on average. Which is pretty typical. I think that's not too bad. Moving on from that. A2, we talked about it last time. It is due Friday of next week. I updated the constraints on the website so that basically it is, when you're trying to pick out two different tones that are in there, it is plus or minus 6 hertz, which means 12 hertz accuracy. Yeah? So I'm hoping that that's a lot clearer now for everybody on the constraints for this next time. I hate turning the lights off. I hate this, but at least the sun's out, which I don't know when that happened, but sometime during the day the sun came out, so that's good news. Okay, so the agenda for today, we're going to talk a little bit more about using the FFT. We're actually going to go into the demo and I'm going to use it. We're going to take a really brief look at filtering in the class, and essentially an in-depth treatment of filtering would take too long, and I don't want to spend more than one lecture on it. So I'm going to talk about filtering and how it relates to the FFT, and I'm going to talk about the difference between operations that happen in the time domain versus in the frequency domain. So when I say frequency domain, I'm talking about the FFT. Is everybody okay with that? Yeah. So I'm going to go through how to use a filter. We're not going to cover filter design in this class, although I will give you resources if you want to create a filter. Where you would go to do that, it's really, really simple. And we'll talk about what a filter is too, just in case you don't know what that is. Okay? All right. So I wanted to go over some FFT examples, right, before we go into the demo here, right? So what I have here is a 1 kilohertz sine wave, okay? So this would be a time series array, and down here is the length and time. I think this is 4,000 or so samples, okay? So this is, you can see that this is a 1 kilohertz sine wave, or you can see that it's a sine wave, right? Goes up and down. Everybody okay with the sine wave? All right. So if you were to take the FFT of this signal, this is essentially what it would look like. We're here, the axis that I have down here is the frequency, and this is the magnitude in decibels. Okay? So what we talked about last time was when you take the FFT, each sample that comes back in this array is a complex number, and the magnitude of that complex number tells you how much of this signal is represented by that frequency. Right? So since this is a 1 kilohertz sine wave, all of the energy is at 1 kilohertz, right? So essentially when you take the FFT, what you have here is this huge spike that happens at 1 kilohertz, right? So it's giving you a way to analyze the frequency content of a signal, right? That's all that it does. And that's what we're going to use it in this class for, is analyzing frequencies of these time series, all right? So let me give you another example. So instead of a 1 kilohertz sine wave, let's say we have a 1 kilohertz sine wave plus a 2.7 kilohertz sine wave. All right? Well, what we get here, this is what it looks like if I were to add those two up, right? You can see I've got two frequencies that are excited here, right? If I were to take the FFT of that, I'm going to get my 1 kilohertz magnitude right here. And then also at 2.7 kilohertz, I'm going to get this spike as well. Right? And so, in a sense, this FFT has analyzed the frequency content of each of those streams. Is that okay? Pretty good stuff, right? Now, all of these signals I generated on a computer. They're perfect mathematical sine waves, okay? So let's see what happens when I actually whistle and take the FFT, okay? So this is a person whistling, it's me whistling, okay? And here is, in the time domain, here's what that whistle looks like, okay? It's not a perfect frequency, it's shifting around a little bit, there's all sorts of noise in the environment, things coming around. If I take the FFT of that, I'm going to get a really good spike. It turns out I'm a pretty good whistler, okay? Right, so here's the frequency content. I was whistling at, call it 700 hertz, okay? But you can also see everywhere around here, it gets really, really noisy in the rest of this, right? And that's because this is a decibel domain, okay? So when you take the log of a number, let's say you take the log of a really, really small number, what do you get? You get a huge negative number, right? So all of these values down here that are close to like negative 100 decibels are essentially 0.0005 or 0.000001, right? They're really small values. So when I take the decibel value, that gets magnetoid. So any of the noise that I had that was down here, that's going to get magnified, okay? So all of this down here is essentially 0, and here's the frequency content of my whistle. Okay, let's say I'm humming, okay? This kind of a thing, right? That actually, in the time series, looks a lot like this, okay? If I were to take the FFT of that, the signal would look like this down here. And you notice that this axis, I've zoomed in to go from 0 to 1200 hertz. Right? I've zoomed in on this FFT. And so essentially what you see here are, I've got a spike here, and a spike here. Okay? What you'll notice here is this frequency is going to be the frequency, basically the most dominant frequency inside of this hum. Okay? You'll also notice that if I take that frequency and I take a harmonic, which is I multiply that frequency by 2, I'm going to get another frequency that occurs right here. Okay? The idea here is when someone is humming, right? Essentially, my vocal tract is essentially there's this thing called a glottis that's at the bottom of my vocal tract, and it's doing this, opening and closing, right? Right? It's the same thing when you do a vowel, like ah, like that. Like so I'm doing that vowel. The glottis is opening and closing. And the frequency at which it's opening and closing is that bass frequency. That's the pitch at which I'm talking. My vocal tract is then modulating all of that, right? So it's got one frequency to work with, and it's just kind of changing how that frequency looks in the time domain, right? So essentially, this is not really a sine wave, right? It's this kind of periodic impulse that's getting shaped a little differently by my vocal tract. Well, those vocal tract frequencies show up as harmonics of my glottis, and they can only show up as harmonics for speech, okay? This is just kind of for your own interest to help you understand what's going on here, right? Here's another example, me humming again, except this is more of a kind of a thing. You'll notice, again, this looks nothing like a sine wave at this point, but it's periodic. And because I have this periodic repeating waveform, I'm going to get different harmonics, right? So I've got a frequency that's decided here, another frequency, which is double that. If I multiply by 3, I'm going to get this, and then it starts to drop off, okay? Essentially, you can sum together sine waves or cosines, and you can form any function out there. Any function can be represented as a sum of sines and cosines. Okay? And the FFT tells you what sines and cosines you should be adding up to get that value, to get that function. All right? So it's an analysis tool. All right. Let's demo it and run it on the phone so you can see what an FFT looks like. Okay? And go through the code. Now remember, I've created this thing called SMU FFT Helper, which, essentially we're going to take a float array, the magnitude, and a float array for the phase. And then we're going to have the class, the SMU FFT Helper. I'm going to allocate it in this way, right here, where I allocate all of the memory for my magnitude and phase buffer. And then I tell it what the FFT size is going to look like here with K buffer length. That's the size of the FFT. And then when I want to do an analysis on it, I'm just going to give it the input array, and then my magnitude and phase are going to be outputs. All right, so let's do this in Xcode. Questions on this before I start? Very cool. Okay, so let's go back to my Rolling Stones example. Okay, essentially what we did last time was we added graphing capability to this so we could actually see the time series, right, in real time using OpenGL, right? This time, I want to add my FFT class. And I've actually added this SMU FFT helper.h in here. All I did was drag it in at this point, right? So now, the first thing we're going to do is import it. Okay, right? So I've imported my SMU FFT helper. Let's go ahead and create a magnitude and a phase buffer. So float star. I wonder if I have an FFT. Hey, look at that. Essentially, I just put in a little code snippet, which was FFT helper, magnitude, and phase buffer. Then let's go in here and get the setup. So here inside viewDidLoad, I'm going to set up the FFT. All right, so FFT helper equals new SMU FFT helper. Okay, buffer length, is that defined? Okay. So the buffer length that we're doing is 4096. Okay. When you do an FFT, it's computationally most efficient when you do powers of 2. Okay. The way that the FFT works is a divide and conquer mechanism, right? And so it breaks things up. So if it can break everything up into a power of 2, it's the most efficient that it can be. All right. That's not exactly true, but don't worry. Just use a power of 2. For the FFT function that I'm giving you, that is true. Okay, then in the dealloc, I'm going to free that memory and delete FFT helper. All right, good to go. Okay, so essentially what we've done here is I'm going to take this buffer and take an FFT of it. Where should I take the FFT of this? Well, I want to take the FFT every single time I get new samples that are coming in because I want to do real-time frequency analysis. Where my buffer is, my buffer's filling. Yeah, I'm going to do it in the update function here. Okay, I'm going to go ahead and do it right here. So let's do this. So I've got this audio data, right, that I got and I'm sending into my graph. Let's go ahead and just recycle that. Okay, so FFT. Hey. Oh, look at that. So if I'm doing the FFT helper, my forward is, remember this is reserved, just put in 0. I'm going to give in my audio data, FFT magnitude buffer, FFT phase buffer. Was that hard to use the FFT? That's pretty cool. There are optimizations that I wrote in here. You're welcome to take a look at it. This is as fast as you can do an FFT. Okay? So the next thing that I'm doing here is, so the next thing I'm doing here is setting that graph data, right? So all I'm doing is taking the FFT magnitude buffer and I'm going to graph it on the screen, right? Using that graph helper. Let's make sure that I actually have enough graphs to do this. Num data arrays 2. Everybody okay with that? I'm going to graph 2 data arrays. All right, let's see if this builds. May not. It did. Okay, we're going to run it on my phone. I'm just trying to get it on the screen. There. It's having a lot of trouble with this one. Well, essentially it looks like this. I don't know why I can't get it up onto the screen now. It is definitely not allowing me to get on here.
You put it up to the webcam and blow up the video.
Yeah. Wow, that's what a... All right.
It's visible.
It is visible, right? So essentially, here's the time series down here, and then up here is the actual frequency analysis. You can see that this music, this is really low frequency content. It's mirrored. This is the worst demonstration that I've ever done, okay? But essentially, right, you can see all the different frequencies that are excited in here, and it's doing a real-time FFT analysis of it, okay? I'll post this code. Download it, use it. You're going to love it, I hope. All right? All right. Questions on that? Nope. All right. So that is the FFT and how to use the FFT. If you go in here to SMU FFT Helper, you'll see that basically there are things that you can put in when you instantiate this, such as the size. If you don't put anything, it defaults to 4096. The window size you can put in, and also the window type, which you can use a Von Hann, Hamming, Recht, or Blackman, and hopefully we'll get to what windowing is today. Okay. Okay, so one of the things that you will notice around here, especially when you're taking the magnitude of the FFT in decibels, is that there's variance around the actual magnitude, and that's unavoidable when you're using the FFT. Basically, all of that noise that we saw, it was around all the things, even in the examples that I was showing you, on real data, there was a lot of variance, right? Basically, the underlying FFT of the signal might look like this really nice curved line right here underneath, but what you're getting is there's just a lot of variance around it, okay? And there's some good reason for that. What's actually doing is you are drawing from a probability distribution of what that frequency at a certain bin is, right? So there's some underlying frequency distribution that you're drawing from, and the only thing you're guaranteed with the FFT is you'll get the value of that frequency within a certain variance. Okay? If you're interested in it, it's chi-squared with 2 degrees of freedom. Okay? That's the probability distribution. All right? Essentially, it's some distribution that you're drawing from. So if you take, if you have a signal and it's a sine wave, and you take an FFT of it, and then you take another FFT of it at, a little bit later in time, right? You can chunk this up into blocks. So essentially, you take the first n samples and you take an FFT, and it's noisy. Right? And then you let the signal play for a little while longer. So you take the second n samples and you take another FFT. You take the third n samples and you take another FFT. What am I going to do with those?
Combine them.
How am I going to combine them?
The average.
I'm going to take the average of them, right? Because it's a probability distribution that I'm saying with some probability. If I average a lot of probabilities together, I will get closer and closer and closer to the actual value. Right? Right? You don't exactly know that, but these probability distributions have an average value of 0, right? So essentially, if I take more and more and I average them together, I will get a much better estimate of the underlying frequency distribution of that signal, right? Why would this be important? I don't know. If you had an assignment where you were trying to figure out tones and you wanted to get as close to those tones as possible, okay? All right. So it's really good for analysis that way. By the way, this method where you take n samples, this is called Welch's method. All right? Yeah.
So this is the method that, for example, electric guitar tuners use. Like they get a signal and then they take the average to find the closest tone.
It's like a guitar tuner. So it's interesting because when you strum a guitar, it's not a pure sine wave. right? What it is harmonic, just like me humming, right? Which means that that fundamental frequency, that's the frequency of the string. But then, you know, it's moving around. There's all sorts of other frequencies that are moving around in there. And so you'll get harmonics of that, right? And so actually the value of those harmonics determines whether it sounds like a guitar or sounds like a violin or sounds like a drum at the same frequency. So essentially what you want to do on is take that first frequency and then average it over time, right? And that would give you a nice guitar tuning, right? But essentially you'd want to do something very, very similar to this, but you only want to focus on the very first frequency that you see, not the other harmonics of that, because that'll give you pitch. All right, good. Local peak finding. All right, so when you're going through the FFT, you want to find the peaks that are inside of it, right? Right? You want to find out where those sine waves are occurring, right? So if you want to find, how might you actually find these two tones? Right? So the frequency is along this axis, magnitude's along this axis, right? How would you actually go about finding these frequencies? What's the best way?
Yeah, maximum amplitude.
Find the maximum amplitude. Awesome, right? That will give me this right here. Perfect. What if I want to find this one? Find local maxes. How do you find local? So like you could take, you know, if the problem here is that when you take the max of this, right, then you say, okay, I'm not going to look at that frequency anymore. What's the next biggest one? It's going to give you one like right next to it, right? So you want to do local maxima. If you want to find local maxima, what's a good way of finding local maxima?
Derivative.
You could do concavity checks, right? You could look at the derivative. This is the same kind of thing here. We can start taking derivatives and do all this filtering. These are all much too advanced for me.
Well, it's just when the derivative
I want to do this fast. I don't want to worry about the math, right? If I take a derivative, what's the problem with that? I have a distribution of frequencies that are just jumping around everywhere. I take the derivative of that, I'm going to get spikes everywhere, right? So I would have to smooth it out first and then take the derivative.
Oh, you can find where the values are closer together. So, because at some point in the frequency, the values are going to be like 1.9, 1.99, 1.999.
Yeah, like a down up.
Yeah, and then it's going to be.
You could have like a down up threshold where you where you see where you're increasing. These are all great. These are all good things. All good things. Here's one way of doing it. What if you had a sliding window and you went across your entire FFT and all you did was you saved the value of the maximum inside that sliding window? What would that look like? Let's say this was your sliding window. And I just run this across the FFT, and this red line here is the maximum that's inside of that sliding window. How might you use this to find local maxima?
You get flats, so several in a row, and that's a local.
When the values are repeated.
Bam. When that equals the underlying FFT, that is when you are at a local maxima, right? And the width of that window is going to basically give you what resolution you're looking at, right? Is this okay? Right? This is called a dilation approach. Yeah.
Why is the max bigger than the line itself?
So because you're in a sliding window, essentially what you're doing is you're saving the maximum inside of the center, right? You're creating a new array that's the same size as this FFT, right? So these arrays are both the same size. And all you're doing is, as you move that sliding window, you save the center value as the maximum value, right? So if there's a maximum value that's on the left or the right, it's always going to be above that line. They'll never equal each other until you truly pass a local max within that window. Okay? The advantage of this is this will give you as many local maxima as you want. Okay? It just depends on the size of your window. Okay? Computationally, as you're finding a lot of local maxima inside the FFT, computationally this becomes one of the most efficient ones you can do. Okay? And it's easy to use. It's called dilation. This actually comes from image processing, but we haven't gotten to that yet.
So how's it creating the flat line?
At the very top. So what happens is essentially this window starts to come in, and the maximum of this window is the maximum that occurs in the entire function, right? And so as you eventually, until you get out of it, then that maxima is always there. Okay? Happiness, we're all good with finding local maxima now. This will blow people's minds if you use this in the workplace, okay? They're gonna be like, what? Like finding local maxima is a huge thing. This is a great algorithm for it, all right? Okay, what's another problem we have when we're dealing with the FFT and we're trying to find a specific frequency?
You could have two samples that are relatively high, but it's increasing between them. So you need to be able to interpolate a point that's above them.
Yeah, exactly. Okay, hold on. Let me repeat what he just said. Essentially, this might be the underlying FFT that you have. And remember, the FFT is continuous, but we got to do it digitally. So all we get is samples from the FFT, right? And all those samples are spaced equally in frequency. So essentially, this is the peak that we're looking for, right? Here's the frequency of that peak, right? Happens there. But essentially, we've got the FFT is giving us 2 points, and the peak doesn't fall exactly on one of the points from our FFT, right? So when the peak is closer to this frequency bin, that's going to be magnitude 2 at frequency 2, right? Here's the magnitude 1 at frequency 1. If the peak is closer to the other one, say over here, I'm going to get magnitude 1 at frequency 1, magnitude 2 at frequency 2. How might I use this to interpolate the frequency value
First, we need
in
to
between?
decide that it's a local maximum.
Somebody else. Thank you, Matt. Somebody else tell me.
Well, you can look for the values where, like in both samples, where M2 and F2 are the same, and F1, F1 are like close to each other.
Yeah, essentially, I mean, yeah, essentially, if the magnitudes are really equal, that peak is probably right in the middle,
Right in the middle.
right? And as this other one gets bigger over here, the peak is sliding over, it's closer to there. Versus if they get bigger this way, it's sliding over closer to there. We could just do a linear interpolation between them, right? And when I say, yeah, we just assume that they're on a line here. What that means is it's going to look like this. I'm going to have the magnitude of this second one over the sum of the two magnitudes, right? And I'm going to multiply that by the difference between these two frequencies, right? So F2 minus F1 gets me the frequency difference, and I'm going to add that to F1, right? So essentially here, now when M2 is really, really big, right, M1 plus M2, that means the peak is really close over here. And when M2 is really, really small, that forces the peak back over here, right? So this gives you a little bit better resolution on where that frequency occurs, okay? Right? Happiness? All right. Okay, so we've been talking about analyzing static frequencies, right? So essentially, you take one FFT and you analyze it for where that frequency occurs. But let's say in this project, you're going to be taking the FFT multiple times, okay? Lots of times per second. So essentially, you're going to have a lot of different peaks every time you take an FFT, and you go and you find the max frequency that's there, right? You could have F1, F2, F3, all of that. Is that okay, right? If you monitor the frequency and how it's changing over time, right? So how many people looked at the Doppler effect in high school? All right. What's the Doppler effect?
A shift in frequency as you allocate to or away a source of sound, or it comes to or away from you.
Yeah. So essentially, it's a sound that's bouncing off of a source, right? So in these examples, my audio source is going to be stationary. The audio source is the phone, okay? It's sending out a frequency, and it's bouncing off everything that I have that's near me, and it's coming back, right? So if the speakers are generating some frequency, and I hold this over the table, that's going to bounce back from the table onto the microphone, okay? And so that frequency that comes out, it comes off, it bounces off, it comes back. I should be able to measure that frequency, right? The microphone should be able to pick up that frequency. What happens now if instead of the table, what happens if it's my hand and it's moving towards the phone, right? Well, essentially what happens is this. It comes, it bounces off, but now those frequency waves, as they hit my hand and it's moving, they become closer and closer together when they're reflected back, right? Think of this as, same thing. If you were to drop a rock in the middle of water and you had something moving, the ripples that come back, if something is moving, they're closer together. It's a higher frequency when you're moving towards it. When my hand is moving away, it spreads out the frequency. I get a lower frequency that's reflected back. All right? So the actual equation for that, the change in frequency is actually determined by the velocity that I'm moving my hand back and forth. Okay? So the change in frequency is equal to the velocity of the object, in this case it's my hand, times, so the change in frequency is equal to the frequency of the source that I'm generating multiplied by the velocity of the object over the speed of sound. Okay, the speed of sound in air. Okay? I know it's the first equation I've had in this class. Oof. Craziness. So, let me show an example of what this would look like. This is just a video that's going to show, here's the FFT, here's the FFT decibels, and then here is a zoomed in version of this right here. So I've just taken this peak and zoomed in on it. Okay? Here's what the FFT looks like when I've really, really zoomed in. Now what I'm going to do is take my hand and go back and forth like this in front of the phone. Okay? So what we'll see here, do you guys see this? Is that tough to see on the, oh, come on. It looks great here. Essentially what you're seeing is there are peaks that come up left and right. Okay? And they're smaller amplitude. You can actually kind of see it here. Look, you see this? As I go back and forth? There's little peaks that pop up on the left and the right. If you really zoom in, whenever my hand is coming closer, you are going to see a higher frequency peak. Now you'll still see the original peak because it's still picking up that sound source from the microphone, right? It's not just bouncing off my hand. It's actually playing from the speaker straight to the microphone. All right? So you'll see that plus the reflections from my hand. Or if I'm pulling my hand away, it's to the left or the right. Okay? So with your second assignment, I want you to use this to enable interaction from someone, right? So your application is going to have to tell me whether a hand is coming closer, moving farther away, or doing nothing at all. Okay? It'd be really awesome if you told me the velocity of the hand, whether it was coming forward or backwards. That'd be great. You're only going to get within so many bounds. But do something cool with it. All right? You can display it on screen, and that's really cool. If you make an animation happen, oh, that'd be great. It'd be awesome. You don't require to do that. Okay? But have fun with it. Questions on the Doppler effect? If you don't like taking the FFT, you could do a continuous wave Doppler radar with this. If you wanted to do that, that'd be cool. No, it's like no. Okay, fine. Use the FFT. Okay, that essentially covers most of what we're going to talk about with using the FFT. I got to talk about the rest of the FFT. I need to talk about filters. Okay, so we'll get through what we can today, and then I won't talk about filters ever again. Okay, so to understand what I mean when I'm talking about filters, we need to understand a little bit of concept of signals and systems. A signal is a collection of sampled data. It's an array, right? So if we're sampling from the microphone, that is a signal, okay? It could be audio, it could be the accelerometer, it could be the image, right? Can we also have 2D, right? That would still be a signal. A system is an object which manipulates a signal. Okay, so essentially the way that we kind of talk about this, let's say we have a signal x of n, right, which is some signal x, and each point in the array you get by n, right? And I have some output y of n. H here is my system. Okay, so I say x of n is passed through h, resulting in y. Okay, a filter is just a system right here. I've got some filter. I'm going to want to apply it to my signal that's coming in so that I get an output array. So Specifically, filters are systems that manipulate the frequencies of the signals that come in. They don't create frequencies, they manipulate the frequencies. Okay? So certain frequencies pass through, others don't. You can have low-pass filters. What do you think they do? Bam. Filter out the high frequencies. You can have a band-pass filter, right? Which only allows a certain band of frequencies through. You can have a band reject filter, right? Which just for some reason you're like 60 hertz is not getting through, okay? Keep in mind, no filter is perfect, right? There are entire classes devoted to filter design, okay? It's old math, okay? There's no reason for you to do filter design for right now.
Perfect ones, but they're not realizable. So
Then they're not perfect, are they? I would argue they're not perfect. Right? So even if you have a perfect filter, it's infinite, right? So no filter is going to pass everything. It's not going to do everything that you want it to do. It's going to be a balance between the parameters that you have control over. So again, we're not going to study how to design filters, but we at least need to know the properties of them so that if we want to apply them into audio data or we want to apply a filter onto like data coming from the accelerometer, you'll have the tools to be able to do that. Filters and frequency. So you can characterize a filter in a few different ways. The first one that we're going to talk about here is just by looking at its properties in frequency, right? So using the FFT in the frequency domain. Is everybody okay when I say domain? I'm just going to call, when we're dealing with F on that axis, on the horizontal axis, it's the frequency domain. Okay, so filters have these frequency domain attributes, at least we're going to talk about filters that have these frequency domain attributes. They're going to have a passband gain, they're going to have a bandwidth, a stop band attenuation, and a transition bandwidth. Okay? So let's talk about what that looks like in frequency. Right? So here, magnitude, frequency, I'm always going to tell you that. This is the characteristics of a low-pass filter, right here. Essentially, we've got the passband, which happens right here from 0 to F sub C. Okay? And the gain of this filter is this value in magnitude. Right now, the gain of this is 0 dB. What is that? What's 0 dB? That's a value of 1. Amplitude of 1, right? If you take the log of 1, you get 0. Okay? So 0 dB is here. So essentially, it's going to pass frequencies all the way up to F sub C, which is called the cutoff frequency. Then I'm going to have a stop band over here. So from this frequency all the way up to my, that should be Fs over 2, my sampling frequency over 2, I'm going to get this. The value of how many dB down I am right here is my stop band attenuation. Okay? It's how well I suppress those other frequencies. Okay? Negative 20 dB, I'm really suppressing frequencies. Okay? If this was an audio stream, the difference between negative 20 dB and 0 dB is the difference between a whisper and a jet engine. All right? It's a huge difference in magnitude. All right? Good. So this has a pretty good dB down attenuation. It's going to filter out high frequencies pretty well. The transition bandwidth, well, no filter's perfect. So there's some band right here. When I get frequencies that are in between these two, it's going to be attenuated a little bit, but not completely. Okay?
I'm confused.
Yeah.
What is that a graph of?
Oh, so this is a graph of the filter. So this is a graph of the characteristics of that filter in frequency. Right? So let's say if I were to take my filter, I take a Fourier transform of it, this is what I would get. So I take a Fourier transform of my filter, it tells me what the filter content is, right? Is it low pass, high pass, band pass?
And how does the filter actually work? Like,
We're going to do it. We'll do it. Right? So if it still isn't clear after 2 slides, I'll come back to that. Okay? So that's how you analyze the characteristics of a filter in frequency. Filters also exist in time, okay? Because, right, if let's say I had that frequency, if I take the inverse FFT of that, I'm going to get a time series, right? So essentially, what we call the time series of that filter is the impulse response. Okay, so you'll basically hear people talk about the impulse response of a filter, and all that really is the time domain equivalent of the filter. Okay, it's just an array of what that filter looks like in time. The time domain property that we're going to be most interested in is just the length of the filter. Okay, filters have different lengths. You want it to be as short as possible so that you can multiply it by your input. Okay? Okay. So if you want to design a filter, we're not going to talk about it, but I am going to give some links to other tutorials. If you've used MATLAB before, you can use FTA tool to design a filter. If you are familiar with Python, you can download SciPy for Python. And here's a decent tutorial that you can go look at. You can go click on it. And it's basically as simple as this code that's right here, right? I want the number, right? Basically, n is going to equal 61. I want a filter that's 61 points long. And here, design it for me with a cutoff of 0.3. So that's the frequency of that f sub c. All right, 0.3 would be just multiply that times your sampling frequency, and that's going to tell you what your cutoff frequency is. Okay. So how do you apply a filter, right? I said that there's this time domain equivalent of a filter, right? So essentially, one of the things that you could do is you could take the FFT of your filter, right? And you could take the FFT of your signal. You could multiply them together. And then you could take the inverse FFT, right? So you want to multiply them in the frequency domain, right? That would be a good way of applying it. You can do that same operation in time, and it's called convolution. How many people have heard of convolution before? Awesome. So you apply a filter in convolution. It essentially allows you to combine the frequency properties of your signal and your filter. Okay, and the basic principle is that if you do convolution in time, that's multiplication in frequency, if you work at the math out, right? Convolution in time is multiplication in frequency. Convolution in time is multiplication in frequency. Okay? What is convolution? It is this. Okay, so I will give a graphic representation of this as well. Essentially, what it says is your output signal at the value n is equal to x, your input signal, and your filter in the time domain, multiplied together, point by point, over a window, right? So basically, I have a window, and if I want the nth output, I'm going to take my filter, I'm going to reverse it in time, do a point-by-point multiplication with my signal, and add up the result. Okay? That's convolution. So to make that a little more clear, let's say that my input is this right here. It's these samples. And here's my filter, h of I. h of I looks like this. Okay? Well, the first thing I'm going to do is reverse that so that I get h of negative I. Right? So I just reversed it in time. Okay? Now, if I want to get the nth output, I'm just going to multiply that reversed filter multiplied times my input. So these overlap right here, right? When n equals 0, I'm just going to multiply these 2 points and add it up. That's what I get. For n equals 1, I've got 2 points that I need to multiply together and add up. Etc., etc., etc. That is the filtering operation. Okay? What happens now when I get to the end? Well, I actually keep going until my filter is all the way done. Right here, right? So now it's all the way done. So essentially, what I've done here is I've taken my length n signal, I've taken my length m filter, and I've generated an output. What's the length of my output?
N plus M.
N plus m minus 1. Good. Go through it, and you'll see. It's n plus m minus 1. All right? If you go through it. Okay, so once I've done that, essentially what I have done here is multiplied the frequency content of both of those signals, right? So even though I have this weird-looking filter in the time domain, if I use convolution and multiply it by my input, I've multiplied their frequency together, right? So that could be a low-pass filter, high-pass filter, whatever you want right there. Whatever filter you want. It could be a derivative filter.
So basically, if you want to filter out, for example, the high frequencies, you would make a filter that contains a lot of low frequencies that when it's multiplied, it reduces them? Or?
Yes. Essentially, what you'd want is a filter that has really small high-frequency values, right? Because when you multiply them, any high frequencies that were in the original signal are going to be really, really small now because you've multiplied them by something close to 0. Okay? What is the time domain complexity of this? Essentially right here, for every single output sample that I want, I have to multiply this and this in a window. What's the time complexity of that? What's the big O notation for that?
N squared.
Close. N times m, right? If the filter is a different length than the signal, right? It's the length of your input multiplied by the length of your filter. It's n times m. All right? So the efficiency of convolution isn't all that great, right? Right? Big O notation of n times m. So essentially what you can do to make this better, if you want to convolve two signals together, notice I said convolve here, not convolute. All right? Convolution isn't convoluting. It's convolving two signals together. All right? Well, we just use this property that convolution is time is multiplication in frequency. Why not just multiply them to begin with? Right? What if I did this? What if I have my input signal and my filter, and I take the FFT, I said DFT here, discrete Fourier transform, instead of fast Fourier transform. They're identical, except one's more computationally efficient. All right, so I take the FFT of the signal, the FFT of this, multiply them, and then take the inverse FFT to get y sub n. Right? If you want to do filtering this way, you can, absolutely. And it will work. And actually, it is more computationally efficient when you have a large filter. How large? You know? Once you get to a filter that's more than 32 samples is about the break-even point, it's more efficient to do this in the frequency domain than it is in the time domain. Okay? Wireless people. Okay, fair enough. If you're going to use this method where you actually take the FFT of the signal and the FFT of your filter, however, it's not going to work out exactly as you planned if you just take the FFT and multiply them and then take the inverse FFT. And the reason for that is because when you do the FFT, actually it performs this thing called circular convolution, right? And essentially what that means is it causes the tail of your signal to wrap around, right? So when we multiplied those things together, we had this go around like that. One of the things that we didn't really talk about is the FFT assumes that your function that you give it is periodic. That means that you have a function that's right here, and it assumes that that same function occurs throughout time, forever, right? And it does that so that, it essentially does that so that the math works out for the sinusoids that you're adding up, because sinusoids last for infinity, okay? So, what's the solution? Zero pad the signal, right? So, essentially here, when you've got, the convolution that you want to perform is n plus m minus 1 long, right? So you take an FFT that is m plus m minus 1 long, right? So your signal is length n, and you append m zeros to it, right? And now when you multiply that in the frequency domain, the output is going to be n plus m minus 1, okay? If you're doing a streaming application, you have to use this method that's known as overlap and add. Okay, before we go into that, any questions now on what I'm talking about with filters in frequency and in time? No?
So what you just did, you literally just made both of them just link with that and plus and minus 1. Just zero.
Yep. I just added zeros to both the signal and to the filter. All right? So now I can do a point-by-point multiplication in frequency and then take the inverse FFT. Okay. So if you want to do overlap and add, essentially what's happening here is you have a streaming input. Okay? So you want to do real-time processing on all of this data that's coming in. What you're going to do here is break it up into n chunks. Okay? So essentially, I mean, that could be like you've got streaming data, you wait until you have n samples, and now you're going to do some filtering, some processing on it, right? And then the next time you get n samples, you'll do some processing on it again. This is the way to do filtering in a streaming manner. So you pull out those n samples, and you add m-1 zeros to it, right? Just like we talked about, right? The next thing you're going to do is you're going to take the FFT of this signal, right? So you get something that looks like this. And you're going to have the FFT of the filter saved in memory, right? You've already taken the FFT of your filter because you don't want to do that every single time. So you do a point-by-point multiplication. You get an inverse FFT. That inverse FFT gives you an output, which is m plus m-1 long, which we just talked about, right? But now you've got another n samples that have come in. You do the exact same thing, right? So you take this, bam, you do the inverse FFT. You've got n plus m-1, and you keep doing it. What's the problem here? Right? So for each n samples, you're getting an output, which is n plus m-1, right? You are generating way more output than you are input, right? So the way that you combine these blocks is something called overlap and add, right? So the output, if there's nothing else here, you just copy the output over. Where you have some overlap in time, essentially the first m-1 samples of this block and the last m-1 samples of that block, they overlap. You add them together to get what the output should be. Copy, add. Copy, add, etc., etc., etc. And you can apply that in a streaming manner, right? I'm sorry, this is dense stuff, but it's something you have to know if you want to use filtering. Okay? Questions on overlap and add? Pretty easy to do. Okay, so now that we've talked about this, I've told you that convolution in time is multiplication in frequency. Okay? Windowing is something that's used in the time domain. And essentially what happens here is multiplication in time. So if you take two signals and multiply them in time, what you've done is convolution in frequency. Okay? They are analogs of one another, right? So does everybody get what I just said there, the difference? Multiplication in time is convolution in frequency. Right? Convolution in frequency is completely unavoidable. If you take the FFT, you have done convolution in frequency. Why? Because we can't take an infinite, it's like up on the slide. Because we can't take an infinite FFT, essentially. Okay? So let's say you've got some signal. Your signal is X right here, right? That signal exists forever, right? It goes all the way to the beginning of time to the end of time, right? That's your signal. But you can only take a finite duration FFT, right? So by just grabbing, 1,024 samples, you've essentially taken that signal and multiplied it by a rectangle, right? So even though this signal, if you were to take, the ideal FFT of this signal, maybe it's really, really nice that it's got, it's the sum of two frequencies, this one and that one right there, and they're really close together. It's a nice peak in the FFT. The second that you just took 1,024 samples, you've now taken this frequency spectrum and convolved it with something that looks like this. The reason that it looks like this is because the FFT of this window, this rectangular window, looks like that in frequency domain. So if you take the FFT of this thing right here, you get that. So now, when you multiply those together in time, and you're taking the FFT of this signal, the output, 0, 0, looks more like that. All right? That is why the FFT has a lot of this spectral widening of the frequencies that are there. Is that okay? Multiplication in time, we've convolved in frequency. The only thing you really need to know here is that this right here, that's the FFT of a rectangle function. This is a rectangle function. Yes, this is called a sinc function. Okay?
And what do the bars represent again?
These right here,
Yeah.
just samples. They're just digital.
Are those like frequencies? I don't.
Oh no, this is all of this right here is time domain, right? So like in time, this is just an array of values, right? So we can only take an FFT of say 1024, 4096. So we have to grab those samples. So essentially what we've done is multiplied that array by this rectangle, right? An array of all ones. All right? So the second that we multiply those in time, we've done convolution in frequency. Okay. So there's a couple of other things that occur because of this thing. This is known as spectral leakage. All you have to know really right here is, again, this is the frequency transform. Frequency transform of a rectangle function. So the bigger that this rectangle is, essentially forces this lobe to be smaller. Okay? Right? So if this is the, both of these have the same exact frequency transform, it's just this one, the frequencies are a lot closer together, right? So if you were to convolve that with something, you would essentially have less spectral widening, right? Because it's a smaller main lobe that you're multiplying it by. So that's good. That means you can take a longer FFT and get better frequency resolution, right? But there's one thing that's bad about this, and it's these things right here. Let's say that this is the actual FFT of your signal. Looks like this in the frequency domain. These lobes right here are really high, right? They're of good magnitude, right? So the second that those lobes start to overlap with anything, right? Because you're doing convolution, you're multiplying and adding up everything. So it's your signal plus these lobes that you didn't really want to be there. So essentially what happens if these have too much energy in them, when you do the convolution right here, so I'm going to take these and I'm going to do a point-by-point multiplication and add them up to do convolution and frequency. Essentially what I've done here is this huge frequency right here. It has a lot of energy, was always overlapping with some of the lobes that were dying out, right? And so when I multiply and add all of those things up, the convolution and frequency, I've essentially washed out this other frequency that occurred down here. Is that okay? Right? Because there's always a little bit of energy in those lobes. So when I multiply and add them up, I always get a little bit of energy, and that energy is more than this other frequency that maybe I was interested in. The solution to this is to use a different window, right? Instead of using this rectangular window right here, well, let's use something that has lower lobes on it. Actually, let's use something like this. In the time domain, this window might look like something like this. In frequency, those lobes have gone way down. Okay? It's a trade-off. You can't get those lobes to go down without making the main lobe wider. So it's always a trade-off. If you want that leakage to go down, your frequency resolution has to go down as well, because this main lobe is now going to be correlating as it convolves over the entire signal. Okay, so when you do something like that, and you do the FFT of it, well, that convolution actually allows you, yeah, you've still got some spectral leakage that's coming down here, but it allows you to hone in and see this frequency that occurred. Okay? So, in SMU FFT Helper, if you want to use some windowing and have it apply it for you, now you understand what it does there. You can do this thing. Which window to use? You can use a Hamming window, you can use a Von Hann window, or you can use a Blackman window. Okay, those are the three ones that I've implemented for you. You can also use a rectangle window, right? The rectangle window has the best frequency resolution and the worst leakage. All right. So you might still want to use the rect because you get the best resolution. If you do want to get into it, the optimal trade-off for a given, if you have a given bandwidth, a given frequency resolution you want to work with, you can look up this thing called a discrete prolate-spheroidal sequence, DPSS, or Schleppian taper. I don't know why they name these things the way that they do. All right. But anyway, somebody came up with it and they really wanted their dissertation to have this in it. All right. So essentially, you can use something like this if you really need it. You won't need it for this homework, but if you'd used that, I would be super impressed. All right. Next time, we're going to go over core motion. I'm going to talk about the M7 coprocessor. I'm done 8 minutes early, which is ridiculous to me. All right. Questions about what we've gone over today? Lots of questions. Essentially, I've given you a lot of information, right? And it's going to take you a while to digest it.
I have one question because I think it was the only thing. What's preventing you from taking a rectangle function in the frequency domain and just zeroing out everything except for the small window that you want as a perfect filter?
You already know the answer to that.
Well, yeah, but it's the one thing that hadn't been
discussed?
Yeah.
So essentially, the problem with that is that is an ideal filter, right? Let's say you wanted to zero everything out, right? So you just go, okay, everything above F2, right? Everything above 300 hertz, I'm going to make 0 in the FFT and then take the inverse FFT of that. Okay? Everybody see that? That is an ideal low-pass filter. It only lets, frequencies below 300 hertz through. And everything out, I'm setting to 0, and then I'm going to take the inverse FFT, right? The problem with that is that, again, you have this problem with multiplication in frequency is convolution in time. And the inverse FFT of that rectangle function in time is a sinc function, all right? It's the exact same that we just talked about, right? It's this kind of thing. It lasts forever. So what you've done here, if you take the inverse FFT of that, you're going to see all of these ripples that occur because you've now taken that and convolved that in time, right? So that's why you have this transition period inside of your filters, is to avoid a lot of that ripple when you're doing filter design. Okay, so don't do that, essentially. They're huge ripples. They're huge ripples, right? This isn't a filter design course, though. If you want to try to avoid those when you're doing filter design and you're using MATLAB or you're using Python, use the Remez algorithm, okay? It's also Parks-McClellan. Use the Remez algorithm, and that will minimize the ripple that you get. Okay? What?
I'll ask you. I wanted to know what that was because I never heard of that.
You never heard of Remez? Oh. Okay. Questions? 6 minutes left. All right, like if you go over here into SMU FFT Helper, is there 16 minutes left?
Yeah.
No way. What should we do here? Should we add something? I just like blazed through all of that information then. I apologize. Let's talk about homework. Okay, so lab time is basically going to start right after this. I want you to get the frequency of the 2 loudest tones that are being played. Is everybody okay with that? If you want to generate those tones, I would essentially, you can go onto like a MIDI keyboard or something and play it from the laptop. When I test your algorithm, basically you're going to be taking an FFT and try and zooming in and tell me what frequency this tone is really at, right? So you're going to use all of the algorithms that I've really talked about, right, in the FFT to figure out what that frequency is. I'm going to take my phone and I'm going to play 2 different tones. And I want your app to tell me which 2 tones are being played. Okay? Maybe if I whistle, I want you to tell me what frequency I'm whistling at. Right? I want you to tell me what frequency I'm whistling at. And then with module B, I want you to use that Doppler effect to really enable interaction. Okay? And it's going to be quick interaction, right? Like I'm gonna do this at your phone. I'm not going to do this. All right? That's not going to show up in the frequency domain very well, right? Because the faster the velocity is, the higher that frequency is going to spike, right? The higher you're going to see these reflections that come back, right? So I'm going to do this or that, right? Or I might do something like this.
When you made your demo, how fast were you?
About 6 centimeters a second. Pretty fast. Okay? That's it. That's all I got. We can be done early. We can go straight into lab. All right? I'll try never to be done early again, guys.